Hello and welcome to part 2 of the series on electric circuits. I hope you enjoyed part 1, which was an introduction to electric circuits, and I hope you learn a lot in this part, which will be focusing quite a bit on resistance and some calculations involved in electric circuits. So what is resistance? It is the opposition to the flow of charge. And remember, as we discussed in the previous video, the flow of charge is also known as current. Resistance is measured in ohm, which is shown by this symbol over here, and 1 ohm equals 1 volt per ampere. So it's pretty much a way in which we can calculate resistance. Electrical energy is converted into heat and light. That is what happens as a result of resistance. Resistance is experienced when electrons moving through a conductor collides with the particles of the medium, and so it's quite a physical thing that takes place due to the electrons, and there's a whole lot of energy that the electrons have that they obtain from the battery, and as they move through conductors and particularly appliances and resistors, they will collide with each other. And that kinetic energy is converted into different forms of energy. And a good example here is that of a tungsten light bulb. It's a material that has a very high resistance, and what we find is a whole lot of collisions here, a build-up of heat taking place, which usually results in light being emitted, which is quite useful. A definition, another one, of resistance is the relationship between the potential difference across a component and the current that flows through it. So we can use those values to calculate resistance, as we will soon see. So when a battery goes flat, as we like to say, what basically happens is all the chemical energy from the battery is converted to electrical energy, and that is because of the resistors in the circuit that have converted this electrical energy to other forms of useful energy that we require, such as light and heat. So resistance is, okay, here's just a question on resistance. The length of wire is a resistance of 4 ohm, and the potential difference across the wire is 12 volts. So now we want to calculate the current, which is the unknown. We have this information to our disposal, so we make use of this formula over here, and we manipulate it so that we can work out the current. We substitute our values in, and we get 3 amps of current. Then similar question, but a change. What will the current be if the 4 ohm resistor is replaced by a 12 ohm resistor? So this is a resistor that is 3 times the amount of resistance in comparison to the previous resistor. Interesting to see what happens. Again, we use this formula. You substitute your value in here. Your new resistance is 12, so it'll be 12 divided by 12, which gives you 1 amp. So we see that an increase in the resistance from 4 ohm to 12 ohm, which was 3 times the amount of resistance, caused the current to become a third of the original current to 1 amp. Originally it was 3 amps. So that's a very important relationship. Again, current is constant through each resistor. Now we're having a look at resistors in series, and current through each resistor will be the same as the total current, the main current. So because there's only one path, we find that current doesn't split. Current is not divided in a series connection. So that is very important for us to understand. Current is reduced if resistors are added in series. Why is that? Because if you add resistors in series, the equivalent resistance increases, and therefore current will decrease. and that is the inversely proportional relationship between resistance and current in a series connection. It's very important to keep in mind that this is a series connection and it acts differently to a parallel connection. Now, having a look at potential difference in the series connection, series circuits are voltage dividers. So current isn't divided in series, but the voltage potential difference is. So when we have the circuit over here, for example, and we had to measure the voltage across each resistor, the voltage won't necessarily be the same unless all those resistors are equal in their resistance. But the point is, they won't all experience the total voltage, which is what the battery supplies. It will be divided between the three resistors based on the resistances. So how do we work out the total resistance for a series connection? Very easy. You just add them all together, as simple as that. So in this case, it'll be R1 plus R2 plus R3 will give us the total resistance. Here's just another question. Calculate the current in the circuit below for these following resistors over here, and that's the respective resistances. We use this formula, we manipulate it so we can work out our current. You don't have to manipulate it first thing. You can substitute it into this formula if you want to, and then you can work it out afterwards. Anyway, so you substitute your values in and you add all your resistors together just like that, just 3 plus 1 plus 4, and total of 8, 3 divided by 8, and it gives you your current, and that is your total current. Looking at resistance in parallel, this is a little bit different because parallel circuits are current dividers. They divide current, so current will be split between those branches, unlike in a series connection which only has one path. So the total current will be equal to the current measured by this ammeter plus the current in that ammeter plus the current in that ammeter over there. Ironically, the total equivalent resistance of the circuit, so if you added all of these resistors together, which is done differently to a series connection, that resistance will be reduced if more resistors are added. So if I had to add another resistor, R4 for example, to this circuit, it would actually cause the total equivalent resistance to decrease. On the other hand, an increase in resistance of a resistor, so of a single resistor, decreases the current in that particular path. So that is, if I just took R1 for example and I increased its resistance, that would reduce the amount of current flowing through this path over here and won't necessarily have an effect on the others. So just a nice analogy that I like to use. Rivers also have current. The water flowing in rivers have current, and there is resistance potentially for the flow of the water in these rivers or in the streams. So if we had to add more resistance in the form of rocks, for example, in this side, then you'd like to think that the current flowing here will be reduced, won't be as strong as this side that has less resistance. So the current here will be stronger compared to the current over here. So to summarize this analogy, the river current flows well with little resistance on this side, but when you increase the resistance, there will be a decrease in the amount of current. The same will be true if we had to remove resistance, and then that would increase the current flow. It's just an analogy, a nice way of remembering it. So how does potential difference work in a parallel connection? Voltage is actually constant across each resistor. all the resistors in parallel. So what we'll find is all these voltmeters will have the same reading. If we had to connect another voltmeter across the entire parallel connection, it would have the same reading. So the voltage is the same. Voltage is not divided in a parallel connection. Only current is. So voltage across resistor 1 and 2 and 3 are all equal. How do we work out the resistance in a parallel connection? This is definitely different to a series connection. You use this formula over here. 1 over your total resistance or your equivalent resistance in the parallel connection will be equal to 1 over the resistance of the first resistor, second resistor, third, etc. So we'll have a look at examples. If we wanted to calculate the current in the 3 ammeters below, and there's the information for the resistors and the respective resistances, and that is the EMF, the voltage of the circuit. So now, before we can calculate the current, we would have to calculate the resistance. So the total resistance, you remember using this formula, substitute your values in, you'll get 5 over 6 here, but that is 1 over the total resistance. We need to invert this, and if we invert this side, we have to invert the other side as well. And we need to show that we've inverted, and we get 6 over 5 ohm. That is the total resistance in the circuit, which we could use to calculate the total current, but not the current over there, because the current is divided. So looking at the next part here, we want to calculate the current going through that ammeter A1. So that is, remember, 6 volts are both experience the same potential difference, because potential difference is not divided in a parallel connection, and the resistor is 3 ohms, so, or has 3 ohms of resistance, so you get 2 amps going through that ammeter over there. Looking at the next ammeter, we would have to, again we have the same voltage. Now we are looking at, sorry, this is the total, this is the total current, and so the total current is calculated using the total resistance, and you get 5 amps. Okay, working in a bit of a strange order here, but anyway, so ammeter 2 dividing 6 by 2 gives you 3 amps. So we worked out over here before that that's 2 amps. We worked out that this is, now we worked out that is 3 amps. So if you add the two together, you get 5 amps, which is in line with what we calculated before, that the total current is 5 amps. So that's another way of working out the total current. We could have just worked out these respective currents and then added them together to get the total. There we go, just showing you how to add those together. So let's have a look at some mixed resistors. Okay, so we have this circuit over here. We have R1 and R2 that are parallel with each other. R3 and R4 are parallel with each other. But they are actually, when we have a look at these, if we had to compare this side to this side, they are in series to each other. Okay. If we calculate the equivalent resistance in the circuit below, let's first work out the resistance in this one over here. So the resistance in parallel for that part 1, 1 over 100 plus 1 over 250 works out to be 7 over 500, and now we have to invert to get 500 over 7. Obviously you can use a calculator for all of these calculations. For the next part of the parallel connection, substitute your values. You get 11 over 1400, invert and you get that. So now we want to calculate the equivalent resistance of the circuit. So we will add the respective resistances of those parallel connections together to get the total resistance. That's easy because they are in series, so we can add resistors in series simply like that. Again, with use of the calculator is perfectly fine. If we wanted to calculate the current in that circuit, we would just use the total voltage, which is 24 volts. We've just calculated the total resistance, and now we can work out the current like that. Okay, working out the potential difference in each parallel branch, because remember that because they are in series to each other, the potential difference is divided in a series connection, so they won't both experience 24 volts, which is the total voltage. It will be split between them. So we've got the current. We now multiply the current with the resistance in this parallel connection, which we've already worked out, and you get 8.63 volts. And then for the next part, we work out its voltage using the total current, and then using the resistance, which we've already worked out, and we get 15.37 volts. And if we added the two together, we should get 24 volts, because the total voltage is split between the two. That is if there's no internal resistance in these batteries, which is a topic that will be covered in the next video. So thank you very much for watching part 2 of this series, and I look forward to going through part 3 with you, which I mentioned would be on internal resistance. See you next time.